Okay, we'll now move on to a section of the algebraic extension of field extensions, which is that of algebraic extensions. So here's like subsection 1.3.6. This is called algebraic extensions. Of all the field extensions, these will be the ones that we're going to be studying throughout this course. So let's begin as usual with a definition. Definition 1.3.7, which says the following. Let K over F be a field extension and take alpha, some element in K. Then we say alpha is algebraic over F if there exists a polynomial, say f of x in fx, such that f of alpha equals 0. Otherwise, we say alpha is transcendental over F. Okay, so the elements will be algebraic over F if you can find some polynomial that have them as a root. So you pick an alpha, you want to check if it's algebraic or not. Well, can you find a polynomial that has alpha as a root with coefficients in F? So here's some examples. For example, root 2 is algebraic over the rational numbers. Obviously you can just take x squared minus 2. That works. Square root of minus 1 is algebraic over the reals. No, we know this. Yeah. Square root minus 1. And okay, for example, pi and e are transcendental over the rational numbers. Notice that these numbers are real numbers, so they aren't transcendental over the real numbers, but they are transcendental over Q. Now let's start studying these algebraic elements a bit more. So here we have the following proposition. Version 1.3.10. Let alpha be algebraic over F. Then we can find a unique minimal polynomial which alpha satisfies over F. So then there is a unique monic irreducible polynomial, which I'm going to denote m alpha f of x. So the alpha is the element that I've taken, f corresponds to what field we're working over, and x is just the variable for the polynomial. So this is some polynomial in fx, so it's monic. Monic is important, will be important later on for algebraic integers. Monic and irreducible. So it's some polynomial which has alpha as a root. Moreover, so this because it's I'm going to take it to be like the smallest one, so it has the following property. Moreover, m alpha f of x divides any other polynomial it will divide any other polynomial which has alpha as a root. So yeah, this, as I already mentioned, this is called the minimal polynomial. Yeah, polynomial of alpha over f. The over f is important. The minimal polynomials can change depending on what field you are working over. For example, up here, root 2 that has minimal polynomial x squared minus 2 over the rational numbers, but if you were to look over the real numbers, then the minimal polynomial would just be x minus square root 2 because root 2 is an element of R. So the field that you're working over does really matter, so you have to be careful. So let's prove this proposition. So as I mentioned, let's take alpha f of x to be the polynomial of minimal degree having alpha as a root. Obviously, I'm taking polynomial. Let me just write this here. Polynomial in f of x. Just alpha of a root. So I claim that once if I go through all the polynomials and check all the ones that have alpha as a root, and just look the one with the smallest degree, that this one works. Note that. So I mentioned that I wanted my polynomial to be monic. I can do this because I'm working over a field, so I can always just multiply through my my leading term and make sure that my leading term is 1. So making it monic is easy. Note that since we are working over a field, imagine that you'd taken your minimal polynomial looked like a n x to the m plus something. Well, I can always just multiply through, because I'm in a field, every element has an inverse, so I can always multiply through by a n to minus 1 inverse times my polynomial, and then the thing that I get looks like x to the n plus a bunch of other stuff. So yeah, okay, maybe I'll erase this, but you get the idea. Okay, so this is our candidate for a minimal polynomial. We need to check that it's unique and that it's irreducible. So let's check that it's irreducible. If m alpha of f x was reducible, we would have, it would have to factor. So m alpha of x would have to look like f of x times some g of x, with f and g and fx. But then what happens if you evaluate this at alpha? So we have f of alpha times g of alpha would have to equal m alpha f of alpha, which we know is 0 because alpha is a root of this polynomial. So now we'd have two polynomials. So when you evaluate them at alpha, the product is 0. Because we're in an integral domain, this means one of these things has to be 0. So it means that f of alpha has to, so this implies f of alpha equals 0, or g of alpha equals 0. But I've taken m of alpha to be the one with the smallest degree. This is a contradiction because I've had a factorization. Now one of these two things contains alpha as a root, but it has to have smaller degree than m of alpha, so that this can't have happened. So since m alpha of f is of smallest possible degree, either f or g has degree 0, i.e. it's just a constant, therefore m alpha of f is irreducible. Remember that for it to be irreducible, it means that if it factored, one of the two things would have to be an element of degree 0. Great, so this middle polynomial is irreducible. So now let's just check that it's unique. So it remains. Check that it is unique, but here again we just use polynomial long division. So note that if f of x is any okay. I had a claim. There was one more claim that I stated in my theorem, which was that moreover m of alpha divides any other polynomial in f of x which has alpha as a root. I'm going to just prove this, and from this we'll get the uniqueness. Let me just check that it's unique. So note that if you have any other polynomial with alpha as a root, so if I have any other polynomial, by my minimality of m of alpha, m of alpha will have to have degree smaller than f of x. So I can divide f of x by m alpha as a root. Note that if there's any polynomial, okay, we can divide by m alpha f, i.e. we have f of x equals q of x times m alpha f of x plus r of x, plus some remainder, with, crucially, as usual, the degree of r is less than the degree of m alpha f. This is what division with remainder means. But now you can see what I'm going to do. I'm just going to evaluate this expression at alpha, and then you're going to get that r has to be 0, so it does actually have to divide it precisely. So now, if we set x equals to alpha, we see, because f of x has a root, we see that r of alpha has to equal 0, but this can't happen as the degree of r is strictly less than the degree of m alpha of f. So r is just 0, therefore m alpha of f divides f of x. Great. So now my minimal polynomial will have to divide any polynomial which has alpha as a root. So from this we just get uniqueness by just assuming that we had two of these things, then one would have to divide the other, and they would each have to divide these themselves. So you're going to get the uniqueness. So using this, we get uniqueness by noting that if I had m1 and m2, two minimal polynomials, then they satisfy all the properties that I've given to m alpha of f. In particular, they both have alpha as a root, and so we would have m1 divides m2, and m2 would have to divide m1. Just the same proof that I've done here. So you get m1 of x would have to equal, say, some constant times m2 of x. But now, remember that my minimal polynomials are meant to be monic. So I can't multiply by just any constant. The only constant I'm allowed to multiply through is by 1. But since mi are monic, because that's what my irreducible minimal polynomial is defined to be, this implies that a equals 1, so m1 equals m2, so we are done. Great. So now we know that there exists a smallest monic polynomial which will always have our algebraic number as a root. Great. great. This minimal polynomial is going to be useful throughout, and we'll figure out some nice ways of actually finding it. At the moment, I've not really told you how to find a minimal polynomial. All I've told you is check every possible polynomial with a root, which has alpha as a root, and then just find the one with the smallest degree. But in practice, that's not the easiest thing to do. In general, it could be difficult to do it, but for the cases that we'll look at, we'll always have an easy way of doing this. So if we combine some of our previous results, we end up with the following corollary. So corollary 1.3.12. If I let K over F be a field extension, and alpha and K algebraic over F, then what do we have? We have fx divided by the minimal this ideal generated by its minimal polynomial. This field is isomorphic to f of alpha, and moreover, the degree of this field extension to f alpha to f, this is exactly the degree of my minimal polynomial. Degree m alpha of f. And the proof, well, this is just combining a bunch of stuff that we have. So I'll just give you the numbers. So this is combine. So this is theorem 1.3.4 plus prop 1.3.2 and prop 1.3.10. So we'd already seen that if you take a field and quotient out by some irreducible polynomial. So if you get a field and you look at the ring of polynomials over it, so f of x, if you quotient out this ring by any irreducible polynomial, you get a field. We then saw that if you looked at a root of this minimal polynomial, then this field was isomorphic to something like f alpha, this is the smallest field that contains f and alpha. And now we've seen that for every alpha, which is algebraic, there exists a minimal polynomial which has it as a root. So now if I come back, this is a minimal, so it's an irreducible monic polynomial. I quotient out my ring by this, and now I get this field f alpha. And we checked that the degree of this extension was the degree of the minimal polynomial, or the polynomial that I quotient out by, as long as it's irreducible. And so we get this equality here. So with all this, we have the following definition: 1.3.13, K over F be a field extension then we say K over F is algebraic if every element of K is algebraic over F. Then we say K is algebraic over F if every element of K is algebraic over F. So why are algebraic extensions so important? Why do we care about them in number theory? Well, you might have a field F which you understand, say like the rational numbers. Now your algebraic field extension, your K, is going to be some field where I know that every element in it looks like, well, I know every element in it will satisfy some polynomial over my base field. So you get some idea of what the elements in K look like by looking at elements in F. You look at F and think, well, let me just look at the polynomials in F of x, and then the roots of these things are going to be the ones that give me algebraic extensions. And so K is just going to be composed of take a bunch of polynomials over F and take their roots. So this is what an algebraic extension is. So in general, this isn't just a completely random extension. I've not thrown in like the number pi or e or something in general. I've only thrown in roots of some nice polynomials. So it gives you some control. So these are some fields which you can have a hope of good understanding. So here's some examples of algebraic extensions. Like our favorite one, so q root 2, this is algebraic. Over q, and 2, for example, the complex numbers is algebraic. Over R. So in general, maybe, okay, you might say, how do I check that field extension is algebraic? That means I have to go through every element in K and find a polynomial which it satisfies. So that seems like a very daunting thing, but actually, it turns out that's very easy. There's lots of easy ways of checking that you have a algebraic field extension. And here's a proposition to help with this. So proposition 1.3.15. Let K over F be a field extension then alpha in K is algebraic over F if and only if there is a, so let me just remind, when I write if with two F's, this means if and only if. If and only if there is a finite extension, the key word here is finite extension of F inside K containing alpha. Great, so I've told you how to check if an element is algebraic. All I need to check is if it lives inside some finite extension of alpha. From this, we'll get like a nice criterion for checking when a field extension, the whole field is algebraic. But let's just do this proof. This proof. So, if alpha is algebraic over F, then we know that f of alpha is isomorphic to fx modulo mf alpha of x. Moreover, this degree by our corollary above is just the degree of this minimal polynomial. So by corollary 1.3.12, and by definition, f alpha is the smallest field containing alpha and f, so it's contained, it has to be contained in K. So if I have an element alpha which is algebraic, then I know that I have this field f of alpha, which is a subfield of K by my definition, and I know that it has degree over F is the degree of my minimal polynomial. So this is f of alpha is a finite extension of F contained in K, which contains alpha contains alpha. So this is one direction. So let's do the reverse direction. So conversely, if alpha is in a finite extension, say L over F of degree n, then just consider the elements 1 alpha squared all the way up to alpha to the n. These are n plus 1 elements, and there's n plus 1 elements in a field extension L over f of degree n, so they have to be algebraically, they have to be linearly dependent because the degree is, so it's a vector space of degree n, and I have, think of this as, I have a vector space of degree n, and I have n plus 1 vectors, so they have to be linearly dependent. Is there n element in a field extension of degree n, so they must be linearly dependent, i.e. there exists bi not all 0, bi in f. Not all root 0, so that such that I can have b0 plus, well, this is b0 times 1 plus b1 times alpha plus b2 times alpha squared dot 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 bn times alpha to the n equals 0. But this proves that alpha has to be algebraic because I now I can tell, here's a part, I can, from here I can figure out what a polynomial is. But this means alpha is algebraic. Algebraic over f, since it's a root of b0 plus b1x plus bn x to the n. So this is a polynomial in f of x. So I've taken an element alpha, which I assume lives in a finite extension. Then by considering these powers, you get a linear dependence, which is like this. And now just change your alphas for x's, and now you have a polynomial, which by definition, alpha is a root of. Therefore, alpha is algebraic over f. Great. So here's a corollary. So corollary 1.3.16. If k over f is an algebraic, is a finite extension, then it's algebraic. So if I want to construct a bunch of extension, remember algebraic extension meant that every element of k is algebraic over f, so every element of a k satisfies some polynomial with coefficients in f. Instead of having to you don't have to go through every element of k and find the polynomial. All you need to check is if this degree is finite. If this degree is finite, then the field that you have has to be an algebraic extension. So this follows the immediate form we have. If you want to have a fun exercise, think of if the converse of this is true, i.e. if you have an algebraic extension, does it have to be finite? Have a think about that. From this, let me just make the following definition. 1.3.18. Say a field k over f is finitely generated. We've already seen this, so I'm guessing we just but I'm just giving this a name. We say a field f over k over f is finitely generated if there exist elements alpha 1, say to alpha n, such that k, I'll say, is isomorphic to f alpha 1 alpha n. So the fields, which are just that you get by just adjoining roots, is roots of some well, I'm guessing by adjoining some elements of k, these sort of fields. Sorry, I shouldn't. Yeah, what I want to say is the fields that you get by adjoining a bunch of elements, say some algebraic numbers or algebraic numbers, will be the ones that we call finitely generated. So if you can get k by just taking f and slowly adjoining elements, so we call finitely generated. So now here's a proposition which you might know if you've done Galois theory, or you might have seen in other guises, but I'm not going to prove it, but we'll use it extensively. This is the Tower law. Which says the following. So let k over f will be a field extension and let alpha I and k be elements which are algebraic over f. I'm going to set fi to equal f adjoint alpha 1 up to alpha I. So I have my so I look like this. Maybe I should just take a finite set, but it doesn't matter. So the first thing we have is fn is the same thing as fn minus 1 adjoin alpha n. And in general, f of I is the same thing as fi minus 1 join alpha I. Just think about what I'm saying here. I'm saying that this, think that this is the same thing as, remember, f alpha 1, alpha n minus 1, then I've adjoined alpha n. So I'm just saying that you can, if you have some field like this, and then you adjoin some extra element, you can just put it inside the brackets. Alpha n is where you put the n in here, and the similar for the previous ones. So if I take this finite generated field and adjoin another element, it's the same thing as I took f and if I had adjoined n elements to it. And secondly, the degree of fn over f, you can work this out successively from the partial degrees as you work up. So this is the degree of fn over fn minus 1 times fn minus 1 to fn minus 2, all the way down to product, all the way down to f1 over f. I'm just going to note f0 equals f in this notation. Okay, so this is the Tower law. I'm not going to prove it, but we'll use it a lot in general. It's quite convenient for figuring out degrees of fields. A lot of the time you might not know what degree of your field is, but it'll be pretty obvious to figure out some of these intermediate degrees, and then you just multiply them together. So here's a theorem to round off this section. So here's theorem 1.3.20. This just follows from the stuff we have before, but I'll write it out. A field extension k over f is finite if and only if k is generated by a finite number of algebraic elements over f. By a finite like this, if I take a bunch of elements that are algebraic over f, some finite number of them, then this sort of this field is going to have to be finite. As long as I've taken algebraic numbers, not if I take anything. The proof, well, we already have everything for this. This is follows from proposition 1.3.19 and corollary 1.3.16. So we've seen that adjoining roots of polynomials gives you finite extensions. Now if you do this a finite number of times, and you're going to end up with a degree which is finite, and so you're done. So this is this, and just end with a corollary, 1.3.21. So if I let alpha and beta in K be non-zero and algebraic over F, then alpha plus or minus beta, alpha beta, alpha over beta, basically everything you can think of, alpha inverse, beta inverse, all of these elements are also algebraic over F. This is quite a nice result. It's given that if I gave you two random roots of some polynomial, it might be tough to check if the inverse of it also satisfies what the polynomial that the inverse satisfies, or what the inverse of the ratio of the polynomial satisfies. And it might be a bit fiddly to do this, but this just now follows immediately from all this dimension stuff from our previous theorem. So I'm just do this corollary. I'll give this a proof. So note that alpha and beta are always contained in this field. This is the field, the smallest field, which contains F, alpha, and beta. So clearly alpha and beta are in here. By proposition 1.3.19, we know F, alpha, beta, because I've taken these things are algebraic numbers, we know that this degree is finite. So by corollary 1.3.16, this thing is algebraic over F, meaning all of its elements are over F. And now just think of, well, all of these elements, oh, no, wrong one. All of these elements that I've written down here, they're all elements that live in this field, right? Because if I have a field, I'm allowed to add, subtract elements, I'm allowed to multiply, divide, the inverse. All of these things are elements inside the field which contain alpha and beta. So they're all elements of this thing, and because it's algebraic, then all of these elements have to satisfy our polynomial. And great, I'll leave it here for this section.